All right, let me begin, right? So we're going to do a quick recap of where we were last class. What was the last topic we were speaking of? Expectation maximization. But even before that, what was it we were talking about? Maximum likelihood estimation, right? So we spoke of generative models, which are basically computational models for probability distributions. Some magic black box that you could shove, and it would generate data which had the distribution similar to whatever data you were trying to model. And we saw some examples of generative models, the category distribution, wrongly called the multinomial PMF in my slides. We saw that this was applicable where the number of outcomes was discrete and finite. If you had discrete but infinite outcomes, you'd need something parametric like a Poisson distribution. For continuous value distributions, you could have distributions like Gaussians and so on. There's any number of distributions that we could actually consider. And in each case, when we wanted to learn a generative model, we had to learn the parameters of this distribution such that the learned distribution best explained our data. So if we want to learn a generative model for some data X, we would choose a model with some parameters theta. And then we want to estimate the theta such that the distribution best fits whatever training data we've got. And the underlying assumption behind the procedure that we followed was that the world was a really boring place, that whatever data you saw was not just typical, it was so typical that if you had to choose a model, you'd pick the model for which the data was most probable, right? And so you selected the data distribution that has the highest probability of generating the data. Now, we saw examples of how we could do this where for multinomial distributions, where if you just work through the simple basic principle, you end up with probability estimates for the different outcomes, which sort of match your intuition, that the probability of any particular outcome is the fraction of observations which had that value. Or if you had a Gaussian distribution, we found that if you just use the maximum likelihood principle, the estimate for the mean is simply the average of your data. The estimate for the variance is the familiar formula for the variance of the data. So all of this seemed to fit nicely. The real issue was when we had something missing, which sort of prevented us from learning the distribution properly. So if this information were available, you could estimate the distribution easily, but when it's not, it becomes challenging. We saw two categories of mechanisms whereby data may be missing. One was where components of the data were themselves unobserved. They were missing. They were censored for some reason. Or something about you had information that was missing about the underlying process that generated the data. So we saw this example where we were trying to estimate Gaussian distributions for a collection of observations. And if you had missing components from the data, then you can't just estimate the Gaussian parameters from this because so many of the data have missing values. And so your data effectively get reduced, right? And biased. So how do you actually account for distributions, for the missingness or the incompleteness of the data? That was a challenge. And so here, according to our maximum likelihood principle, we know that we're only allowed to maximize the likelihood of whatever it is that we have observed. That is what is typical. But the distribution is defined over the complete data, including the missing components. So we had to integrate out the missing components. And that left us with this ugly integral inside a log, which prevented us from estimating probability distributions. Or we had these other examples where there was something missing about the underlying process itself. And we saw a couple of instances. The dice roller example where maybe you had two different dice that were being rolled, but at any given turn, one of them was randomly selected and the number that it rolled was called out. Now, in this case, you don't know which dice generated each outcome. So how do you make the assignment and how do you estimate the probability distribution of the dice? Challenging, right? Or the other example we saw was that of a Gaussian mixture, where in each turn, you randomly chose one of a number of Gaussians, and then drew a sample from that Gaussian. You do not know which Gaussian generated any particular observation. How do you estimate the parameters of all of the Gaussians? And how do you determine the fraction of called outcomes that came from each Gaussian? So again, over here, in both cases, the probability of any observation was the sum over all components. In this case, it was the sum over all Gaussians. And the previous one, it was the sum over all dies of the probability of choosing that component times the probability of generating the observation from that component. So again, the process of generation was a two-step process. There were two random variables chosen. The first was the component. The second was the outcome from the component. And one of these two attributes is missing. It's not presented to you. Therefore, your data are censored. They're incomplete, right? And so here's the general form of the problem. You have data that are missing, or some components of some information about the entire process of generating the data has not been presented to you. So in these cases, the maximum likelihood estimation ends up with an estimate of the form where you have to maximize the log of the marginal probability, which means there's a summation or an integral inside the log. And this makes estimation impossible, right? Or at least challenging. And so this is where EM came in, right? Our objective was to find the model parameters such that the log likelihood of your entire training data was maximized. So the log likelihood of the entire training data, assuming all your data instances are independent, sums over all the instances. And for each instance, it computes the log likelihood of the observed components of the instance, which means that within the log, the unobserved components, which are represented by H to indicate that they are hidden, I may alternately use H or M, these things are being marginalized out. And this, of course, means that you have a summation inside the log. And we went through some effort in the last class to show that you actually end up with, you can end up with a hill climbing algorithm of this kind, where at each point you maximize the joint log probability of the missing and observed components, basically the complete data. And unfortunately, H is not given. So what we will do is to take the expectation over all of the missing components, over all possible values. The expectation of the log likelihood over all components, right? And the expectation itself must be requires a probability distribution to compute. And so over there, we use the current estimate of the parameters to compute the posterior probability of the missing components given the observed data. And then based on these probabilities, you computed the expected log likelihood of the data over where the expectation is over the hidden or missing components. And this is what we maximized. And this was maximized with respect to theta. So that gave us a new estimate for theta, which could be used then again to compute the expectation. So this was our EM algorithm. So there's a two-step process. The first is, it's called the expectation maximization algorithm. So there are two different terms we are estimating over here. First is the posterior probability of the missing components given the observed data and the current model estimate. And the second is the model parameters themselves, right? So what on earth was that? And so here's how the expectation maximization algorithm worked. We'd initialize our model parameters, and then iteratively within each step, first you compute the probability distribution, the conditional probability distribution for the missing components using the current estimate of the model parameters. And then next, you compute the model parameters, re-estimate the model parameters using this probability distribution. Now, this is actually a coordinate ascent procedure of sorts. So one way to think about it is that you can say that I have my model parameters theta, and I have my missing components H, both of which are unknown, right? All you have is the observation. And so you can think of the entire model as the log likelihood as a surface over the space. And in one case, you're fixing this guy, you're estimating the probability distribution along this one. Then in the next case, maybe you're taking the expected value over here, and then you're maximizing along this direction. And then once you maximize this, you stop here, you estimate the probability distribution over there again, and then you get an expectation, you maximize along this direction. So you're going, you're moving up one coordinate at a time. So it's a standard coordinate ascent kind of approach, right? Now, there are two things here. One is how do we compute the posterior probability of the missing components given the observed data? And the second is how do we actually maximize, obtain the next estimate of theta? So I'm going to actually work through this example. I mean, the term work through is a misnomer over here. So I'm sort of going to give you an idea of how the estimation is done before we go off and try to look at it from a more intuitive perspective, right? So here's what we wanted to do. We are given a bunch of rolls of the dice in this dice example, and the probability of getting any particular observation from this process is the sum over all the components, all the dice, of the probability of selecting the dice times the probability of generating the observation from that dice, right? And of course, from this, that's P of O, and P of K comma O is simply the product of selecting the dice times the product of generating the observation from the dice. Now, using this, you can obtain the conditional probability of O given K given O. So this is like saying, I have these two dice, right? One of them has a very low probability of generating the number 3. The other is loaded, so it almost always generates the number 3. If I see an instance of 3, which dice do I think it came from? Then, a priori, you're more likely to believe it came from the dice that has a much greater probability of having generated it. But not in every instance, right? So overall, this is basically saying what is the probability of any given component given the observation, P of K given O. And that can be computed using Bayes' rule. Straight up, yeah.
Is there any way to go about this problem if both of the dice have the same probability distribution?
There is not. You're going to get an ambiguous solution, right? In fact, this is not an identifiable solution in any case. I'm not getting into that, but yeah, that's a very good point, right? So I can compute P of K given O using the probability distribution for the dice and the probability of selecting the dice, right? So the E step is done. Then the second, so this is, I'm calling this P curve, K given O, which is to say that this P of K given O is obtained using the current estimates for the dice and the probability of selecting the dice, yes.
What if the posterior is not, we cannot parameterize posterior with the same data?
In this particular example, we're assuming it, right? Okay. We'll get to that. So the second step is this one here. You have given the P of H given O's. You've already computed it. How do you maximize the joint probability of H and O, the expectation of the joint log probability of H and O, given the posterior probabilities? And in the case of dice, you can just write this out. You are maximizing this term over theta. This is the sum over all observations. Within that, you're taking the expectation over the components, so sum over all H's of P of H given O times log of P of O, right? Which is just P of H comma O. And if you work that out, this is the expectation over sum over all observations of the expectation over all components of the posterior probability of the component given the observation times the log probability of choosing that dice times P of O given the dice. And then you have some additional terms over here. What are those additional terms there for? To make sure that all the probabilities sum to 1, right? And you work through it, you're going to get the solution. Fairly straightforward. Nothing particularly complicated. If you actually look at it very closely, everything kind of makes sense. I'm not going to explain why it makes sense because I just wanted to show that the arithmetic is very trivial, right? Same thing over here. So the overall process is going to look like this. You'd have some initial estimate for all your parameters. From those, you're going to compute the posterior probabilities of the components given the observation. Using these posterior probabilities, you can go back and compute the updated estimates for both the dice, in this case, both the category distribution components and the probability of selecting the category distributions. And so there's the E step and the M step. You keep alternating those till the whole thing converges. Or in the case of the Gaussian mixture model, right? How does this work? So here again, within any step, you're going to choose a Gaussian and then generate an observation from the Gaussian. So the joint probability of the Gaussian and the observation is P of K times the probability of the observation given the kth Gaussian, from the kth Gaussian. And so from the joint probability, I can compute the conditional probability of K given O, right? Bayes rule. Nothing particularly complicated. You would know how to do this. And once I have the conditional probability, then I have got P of K given O using the current estimate of the parameters. So this was easy. And then from those, I now have to maximize the log likelihood or expected log likelihood of my complete data, where the complete data associates a Gaussian with each observation, right? And so when you work through the arithmetic again, I can just write this down. P of H comma O is log of P of H comma O is the log of the probability of choosing the Gaussian plus the log of the Gaussian itself. Again, I have an extra Lagrangian to make sure that the probabilities of selecting the Gaussian sum to 1. And this can be maximized, right? Straight up. Differentiate, equate to 0. You're going to get your standard formula for the means, which is standard EM formula for the means of the individual Gaussians, for the variances of the individual Gaussians, and the probability of selecting the individual Gaussians. No biggie. And so the E and the M algorithm steps are going to switch between these two. In the E step, you're computing the posteriors. In the M step, you're using the posteriors to in the expectation formula to re-estimate the model parameters. So far, so good. I've just sort of flown over this. I didn't spend a lot of time. We'll spend more time on it again in the next few minutes. Any questions? I'm assuming most of you are familiar with much of this, right? All right, Hari. First statement, true or false? True. Okay. What about the second statement, true or false? False. The third? True or false? False. And the fourth? True. So the E step computes the a posteriori probability distribution of the missing variables. The M step maximizes the expectation over missing variables of the log probability of the complete data. So far, so good, right? I mean, kind of makes sense. I don't see the missing data. I'm going to assume they are there and compute my log likelihood. And then I'm going to take the expectation over over the missing components. And this should kind of give us my next estimate. Intuitively, it makes sense. So what does this practically do when we have missing data? What is the intuition behind how it resolves the problem? So that's what we're going to spend some time on. Let's look at the missing information problem again. And in this case, I'm going to be looking about that again. There are two categories of missingness. One is where you have missingness in the data itself, and the other in which you are missing some information from the process that generated the data. So let's look at this. Here's my problem, right? I have this collection of incomplete vectors. How am I going to compute the parameters of a Gaussian using these incomplete data? Now, we are given the set of observations. For each vector, you have some observed components. You're missing some components M, right? And the complete data for any vector is going to include both the observed and the missing components. But the complete data are not available. We do know how to compute the Gaussian if I have the complete data, right? So given this, if I gave you no math, what would your best guess be to how to handle this, as to how to handle this problem? There are holes in my data. What do I do? Sample? Yeah, basically sample it for what purpose? So basically, let's look at a single vector. You want to fill in that value, right? We know that if I know this value, I'm going to be able to compute my Gaussian trivially, right? The real problem arose because, and you're right? These data are missing. So how do I fill in this missing value? What do I stick in there? Sampling from the other samples. Can you be a little more specific? Alex, you need some coffee? Okay. So how do you go about this? But those are different components, right? One might be the height of people. The second component might be the weight. How can you sample from the Gaussian of height? Yes, Justin. Sample from which most likely Gaussian? Right. So here's the thing. Just think about this again. I have heights and I have weights of people. These are two components, but I was missing the weight, right? So can I just sample from the Gaussian of heights? No. What would I be sampling from? Suppose I told you that tall people are heavier and short people are lighter. Then what would you be guessing from? Pardon me? Thank you, right? I'm going to be saying the way I'm going to fill this data up is to fill it with every possible value. Think about it this way. Here's a different way of looking at it. I give you this vector over here, and that it's missing this component, right? So I make a bajillion clones of it, or just think of this alternate world where I've seen a bajillion instances of the exact same vector, and in every case that component is missing, right? Then if I asked you, what can you tell me about that component? Is it always going to be the same in every instance? No. What is it going to be? It's going to have a distribution, correct? And what would that distribution be? What kind of Gaussian? So again, let me go back and give you this example of tall and short people, right? So is there a chalk somewhere here? Thank you. So let's say these are tall. This is tall, short, heavy, and let me call them, for want of any word, light, right? So let's say amongst tall people, I have, let's say for some person, the height is missing, right? I've just given you the weight is missing. I've just given you the height, right? So, and that person happens to be tall. Okay. And say for tall people, the distribution of heights, 90% of tall people are heavy, 10% of tall people are short, right? So I've given you this 10, tall. This is what I've given you for everybody. Are all of them going to be the same weight? Yes or no? So then what is this weight going to look like? Gaussian? This is the table I've given you. What's it going to be like, Trana?
Still be a Gaussian, just center elsewhere?
Where's it Gaussian? I've literally given you this table. I'm saying people can be either tall, heavy or light. They can be either tall or short. And amongst tall people, 90% are heavy and 10% are light. Right? So what is this? What can you tell me about the weight of these people? All of them heavy? It's going to follow this distribution, is it not? Right? I'm going to see H, 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 and then I'm going to see 1/10 of them are going to be light. Correct? If I'm following the statistics of the data I'm familiar with, isn't that how you'd expect it to be? That makes sense to everybody? Right? So when I fill this data up and I complete the data in every possible way, what am I going to see? Am I going to see just one single value of the missing component? I'm going to see every single value of the missing component, correct? But how frequently am I going to see that missing value? Any particular missing value, how frequently am I going to see it? It's going to be observed according to the conditional probability distribution of P of M given O. Right? Just following the same example over there. That makes sense? To all of you? Right. So that's it, right? I'm going to see every possible value, but in proportion to the probability conditioned on the observations. Everyone clear? Right. So this one guy, this one vector alone, if I imagined I saw like 1 billion of that same vector with the same missing component, the missing component is going to take every possible value, but the frequency with which it takes any value is going to be proportional to P of M given O. You guys with me? Right? And so here's what I can do. For every one of my data vectors with incomplete missing components, I can scale it up to a very large number. Let's say I'm scaling it up to some n, where n is, each vector with some missing components. I've scaled it up to, say, n, where n tends to infinity. It's a very large number, okay? So I'm going to see this vector, and it's going, now all of these guys are complete, right? And how frequently will I see any single given missing component over here? Pardon me? So this is going to be, so I'm going to see this vector with that particular value m over here, n times P of M given O times, correct? Everybody with me? Where n is the number of times I've scaled it up to. Make sense? No, this is, if n is a large enough number, a law of large numbers, this is what I'm going to be saying, pretty much, right? So is this making sense to everybody, right? If I complete the data infinite times, the fraction of those times where I see any particular value is going to be proportional to P of M given O. And now I have complete data. I've done this for every single data instance. Now I have complete data, correct? And so what is so if I have, let me call this, instead of M, let me call this whatever, L to represent, it's a very large number, right? So now, if I take the average of all of these vectors, right? How many vectors do I have? This is my original set of incomplete vectors, right? For each of those incomplete vectors, I have completed it in every possible way, right? And then I'm going to see O of, let me call this vector of observed, comma, missing, divided by n times m. That's going to be my average, right? Make sense to everybody? Right, okay. But can I simplify this term here? Can I simplify this? I can rewrite this as, for every possible missing value, it's going to be L times P of M given O times the vector of O comma M, right? Instead of summing over all of the things, I've just grouped it by missing value. That makes sense? Everybody? It did not? Okay. So here, this is summing over all possible combinations, right? But in all of these possible combinations, you're seeing every possible missing value. how many times will I see a particular missing value? L times P of M given O, correct? So I'm summing, instead of summing over all the clones, I'm summing over all the missing values. It's going to be L times P of M given O times the completion with M. It's gone out. It's summation over M, L times P of M given O. This is my complete vector with observed and missing components. Right? That makes sense to everybody? So I can just rewrite this over here. I can say L times P of M given O, the vector with O comma M. This is the complete vector. These L's will cancel out. Right? And so voila, I just end up with, and this P of M given O I can say is from a previous estimate. And so I'm just going to end up with 1 over N, summation over all of my observations, summation over all of the missing components, P of M given O times the complete vector. And if M is a continuous value, that just becomes an integral. The formula makes sense to everybody? Right? Very straightforward. When you actually work it out, this is the only way in which it can be done. Everyone? Questions? Same thing for the variance, right? For the variance, what would I be doing? For the variance, I'm going to be summing this over. I'm going to be summing this over all of my observations. For all of the observations, I'm going to be summing over all of the missing values. And there's, of course, the 1 over N times L, right? And this is going to be L times P of M given O. This is how many times I'm seeing any particular missing value. And then this is going to be my complete vector, right? Minus the mean whole squared. This is my variance, right? And the L will go away. And that leaves you with this formula over here. Prana, that makes sense? So where's the incomplete bit that makes you think rather than be certain?
Your brain is moving so much faster than mine. It'll catch up. I'll get there.
Okay, the rest of you guys, did it make sense? The integral of your brains is larger than mine, definitely, right? So did that make sense? Did it make sense to you? It made sense to Adnan. It's got to make sense to everybody. Okay. So that's a very simple mechanism for going about it, right? What did we actually do? What is EM doing over here? What EM is doing is completing the data. You know that you cannot deal with incomplete data. So you're going to complete it. And you're going to complete it in every possible way in proportion to the probability of that particular value. And then you get your estimate. That makes sense? Right? So same thing. So this is where the rest is just notation. The intuition has got to be fairly clear, right? So this one's easy. And you can work out the rest of it, right? Now let's look at a different problem. This is a Gaussian mixture problem, right? In a Gaussian mixture problem, what was the problem again? At each draw, you selected a Gaussian, and then you selected an observation from the Gaussian. And you're saying?
Yeah, I was saying that. So we're not sure which Gaussian we are.
Correct. So because when I look at any particular observation, every Gaussian is likely to have generated it, right? So if you take a look at this instance over here, if I got, say, this draw over here, the blue Gaussian could have generated it, the green could have generated it, so could the red, right? So you really need to know which Gaussian the vector came from. So if I knew which Gaussian each vector came from, then I could just segregate out all the data from the blue Gaussian, estimate the blue Gaussian parameters. I could segregate out all the data from the red Gaussian, estimate the red Gaussian's parameters. And the same thing for the blue Gaussian and the green Gaussian, and estimate the green Gaussian's parameters. I don't have that, right? So I'm going to assume that I have observed the same vector a ridiculously large number of times, right? And so suppose I observe this data point right here. And I ask you, I've seen this 1 billion times. How many of them came from the blue Gaussian? What is your answer going to be? Small amount, yes, but yes, what is that amount? Mhm. There's a posterior probability of blue, right? So if I have, Alex, you're right, but still there's a greater degree of precision than that possible, right? So if I've got one vector, so I have these three Gaussians, whatever. And if my vector happens to be here, all of the Gaussians are capable of having generated that vector. So if I saw this one vector L times, where L tends to infinity, I'm going to see the green vector. This is green, P of green, given vector number of instances, right? So the number of times I'm going to see it is going to be L times P of green given the vector. That makes sense to you guys? Right? So again, if I look at this vector, all I've got to see is, I know that this guy has this probability of having generated it. This Gaussian has this probability of having generated it. This Gaussian has this probability of having generated it. Their scale proportions tells you the posterior probability that of any single Gaussian having generated the observation. So I'm going to assign the color. I'm going to complete the data by assigning the color in proportion to the posterior probability, right? And so that's what I'm doing. I'm completing the data in every possible way. And the manner in which I complete it, the manner in which I choose any particular form of completion depends on the posterior probability of that particular completion, right? And now I have complete data. Except what happened, each data instance became an L, incredibly large number of data instances, right? But then you have this blown up, scaled up version of my data just because I had to complete it. And now I'm going to estimate the data model parameters from the completed data. Yes. Okay. Yeah, I mean, you're completing stuff, yes, but yeah, it's going to look kind of similar, right? So we'll get to that too, right? And now, what about the proportion P of K given O? That can be estimated using the current estimate of the Gaussians and the prior probabilities, right? And so here's what we're doing. Every one of my vectors is going to become many vectors, right? So let's actually see the example, work this out. In my example, there are only three Gaussians, right? If I have any single vector, this vector can become a red vector, a green vector, or a blue vector, right? And if I've seen L instances of this, how many of them are going to be red? Guys, come on, don't wake up. If this is my vector V, I'm missing the color, right? So I've scaled it up and said I've seen L instances of the same vector, where L is a very large number. How many of them would I expect to have come from the red Gaussian? This is going to be L times P of red given vector, right? For this guy. For this one, it's going to be L times P of green given vector. This one's going to be L times P of blue given vector. Correct? Make sense? So I can do that for every one of my vectors. And now, since all the vectors are complete, I can segregate out all of the blue vectors, segregate out all the red vectors, segregate out all the green vectors. I can compute the parameters of the red, blue, and green Gaussians. That makes sense to everybody? Yes. No, I'm saying that hypothetically, right? You just say, if I saw the same vector L times, how many of them are going to be red? How many are going to be green? How many of them are going to be blue? That's it. So you're thinking of that one vector as a representative of a very large, you're seeing that as a representative of, an infinite collection of the same vector. That's it. Right.
we are essentially finding the posterior probability for all the vectors and saying which version is likely to.
We're not picking which is most likely, right? All I'm saying over here is I'm completing the vector in every possible way. I'm actually completing it. I'm saying this, I've seen this vector, right? I've seen this vector once. But my question is, if I saw a very large number of these vectors, how many of them would have come from the red Gaussian? So when I complete it, I'm going to complete it in a statistically correct manner, right? That makes sense? So I'm basically completing the data. I'm making, because my data were incomplete, I'm making the data complete. And I'm completing it by filling in the missing information, and I'm filling it in every possible way, right? And I'm filling it in the appropriate way. The number of times any particular value is observed is proportionate to the posterior probability, right? So now, if I want to compute the mean of the red Gaussian, what do I have? I'm going to sum over all of the vectors, right? But then I'm going to, each of the vectors is going to be, I have made L clones of it, right? For each vector, how many red Gaussian clones do I have? It's going to be L times P of red given vector. These are the number of clones I have, right? Times the vector itself, divided by the total number of vectors is the number of vectors. Each of them has been scaled up L times. This L, of course, goes away, right? Because that goes in. So, and that leaves me with 1 over, actually, no, this is going to be n times summation over V, L times P of red given V, right? This is the number of times that I'm seeing the vector, the red clones of the vector. That makes sense? Right, so this L will go away. You're looking confused. Did I lose you? So this L goes away, right? In fact, yeah. So this is going to be 1 over summation V, P of red given V, times summation over V, P of red given V times, right? This is going to be your updated estimate for the mean of the red Gaussian. Does that make sense through my math, through my errors? Make sense? You're looking lost. Where did I lose you?
I'm trying to visualize like it's slides.
It does this. Okay, I gave you a formula, right? You're sitting far away, but let me just, I have a closed form formula over here. So I'm just imagining that everything has scaled up. So if I segregate out all of the red Gaussians, then for each of my vectors, I'm going to see L times P of red given vector. These are the number of times I'm going to see a red completion, correct? Times the vector. So this is the sum of all the red completed vectors, right? These are the identical clones of the vector, where the only thing that has happened is that I've colored the vector red. And the total number of vectors, of course, is the summation over vectors, L times P of R given V. And these L's will cancel away. So this is literally taking the average of all of the red copies of the vector. It's taking the average of these guys. And to take the average, I have to see how many of this guy do I have from the first vector times this vector, right? Plus how many of this guy do I have from the second vector times this vector? Plus how many of this one do I have, which came from the third vector, times the vector itself, right? I'm accounting for the repetitions. That makes sense? Okay. And so this term over here is accounting for the repetitions. This is the count of this vector coming from V. And this is the total count of all instances without actually multiplying by V. I'm taking the average, right? But the thing that happens is that when I do this, basically you're going to end up with a formula out there where you're summing over all of the vectors, right? And for each vector, the proportion of it that you're not using the entire vector, you're using only just a proportion of it. And you're computing a weighted average of the vector itself, where the weight is simply the posterior probability of the Gaussian given the vector. But it just comes out of the simple intuition that you're asking yourself, if I saw a very large number of instances of this vector, how many of them would have come from red? If I saw a very large number of instances, how many would have come from blue? How many would have come from green? Does that make sense to you guys? Right? Or did I confuse you completely? Yes, Justin.
It seems kind of weird that we're dividing by the summation of L times the probability.
Okay, just tell me this.
Of L.
Okay. How many? We want the average of this term over here, right? But each one of these is actually many copies. How many copies is this?
Just L times the probability.
L times posterior probability, right? So when you sum all of these and divide by the count is L times the posterior probability of red for this one, plus L times the posterior probability of, so that's not going to sum to n. Right? So let's just say that 1/3 of the time the first vector came from red. Or let's just say in every case, 1/3 of the vectors come from red. Then this is going to be L times 1/3 plus L times 1/3 plus L times 1/3 plus L times 1/3, right? So the posterior comes in. Does that explain your question, Doc? No. Okay. So I'm failing at this miserably. So give me another chance, right? We have a little time. So I'm going to take just two vectors for my example, okay? I have my one vector for which the Gaussian index is not known. Suppose I had 100,000 copies of this same vector, right? How many of them would have come from red? So this is going to be these many, right? Where this is going to be 100K times P of red given vector, correct? And then I'm going to get these many, assuming there are only two colors, right? And this is going to be 100K times P of, say, green given vector. So Justin, you with me so far? Right. So let's just focus on the red portion of it, this one. How many of them do I have? 100,000 times P of red given V, right? What is the average of all of these guys? What is the sum of all of these guys? All of them are the same vector, right? So the sum is simply going to be V times 100K times P of red given vector. You agree? The sum of all of these guys. Everyone with me? Right. Let me call this vector V1. So this is going to be V1, right? So this is V1. Similarly, if I have another V2 and I scale it up, how many am I going to get from this one? That's going to be V2 times 100K times P of red given V2, right? You with me on this? Right. What is the total count of red? The total count of red is this count, which is going to be 100K times P of red given V1 plus the similar thing over here, plus 100K times P of red given V2. Is that making sense? Justin? Right? This 100K is irrelevant, right? It's just a scaling factor, it goes away. So when you do that, you basically end up with this term which says I'm summing over all the vectors, and the denominator is the sum of the posterior probabilities of the Gaussian, and the numerator is the sum of all the vectors weighted by the posterior probability. Did that clarify any? Right? That clarify things for you guys? Yes. We got it from the previous estimate of the model, right? And same thing, right? When I want to do the variance, instead of averaging the vectors, I'm going to be averaging the vector times vector minus mean whole squared, right? So for the variance, you end up with the basic same formula, which is to say you're going to be computing the weighted average of the outer product, centered outer products of the vectors in exactly the same manner. So did that make sense to how what we did? So what was the basic thing we did over here? When you had incomplete data, what is it we're actually doing? Pardon me? We are filling in. Here's the thing I want you to remember, that the arithmetic is kind of not is all very fine, but the key is that you're filling in the data, the information that you do not have, and you're filling it in a statistically plausible way. And then once you fill this in, you can go ahead and estimate the parameters that you could have estimated if the data was not incomplete, right? So what's going on here? Here's the overall EM algorithm for estimating Gaussian mixtures. You'd initialize all the means and variances for the Gaussians and also the prior probabilities of the Gaussians. Then you're going to compute using the current estimates. You're going to compute the posterior probabilities for all of the Gaussians, which is basically the proportion of each observation assigned to each Gaussian. And then you can just use your standard counting formula to go ahead and get your updated estimate for the means and variances and the proportions. Then you can use those and go back and re-estimate your posterior probabilities. And the intuitive expectation is that when everything is stable, when you've got the true distribution, the posterior probabilities must basically give you back the same distribution as parameters as before, right? So it will converge. That makes sense to everybody? Right. So now, here's the key piece. The general EM principle is that we completed the data by considering every possible value for the missing variables, right? And in proportion to their posterior probability. And then once you completed the data, you just went ahead and estimated your parameters. And this is the easy bit, right? Once you get this notion in, the rest of the arithmetic doesn't matter, does it? Right? Because what was the key? What was the key bit over here? What was the really key magic trick? What was key to getting the solution here? Filling in the missing data, right? This was just one way of filling in the missing data. Can you give me another way of filling in the missing data? Yeah? Averaging, is that a statistically plausible way? Yeah, that's one way of doing it. Something else? Some other mechanism of filling in the missing data. Pardon me? Most occurring value. That would give you something like k-means. Any other way of filling in the missing data? Right? I can complete the data by sampling, right? Which was the first thing that Mehal mentioned. That if I have the posterior probability distribution for P of M given O, then I don't need to make infinite clones of that vector. I can make just one copy of it where I fill in the missing data by sampling. And if I have a sufficient amount of data, the estimate should still work, right? And it's statistically plausible. That makes sense?
If
the data are large enough, they're going to give you basically the same solution. Right? Yes.
Your sampling, do we need to take some K times?
You can. It's enough to do it once. Doing it more than once is probably going to give you a more robust estimate, right? So if you're sampling, clearly making just one copy of it is going to be noisy. You can make many copies of it. The more copies of it you make, the better your estimate is going to be. But again, that too is EM. When I'm sampling from the posterior probability distribution, I'm actually performing expectation maximization, except I'm doing this using a Monte Carlo method. Right, everyone with me so far? So in this case, you're completing the data by sampling possible values for the missing data or variables from the conditional distribution. And then you're re-estimating parameters using the complete data. Okay? So overall EM principle, just remember this. Initially, either some data or some information is missing. You're going to initialize the model parameters. Then you're going to complete the data according to the posterior probability computed using the current model, either explicitly by considering every possible value, but this only makes sense if that gives you a closed form formula where, the scale up disappears, right? Very often it won't. So an alternate cheaper strategy is to simply sample the posterior probability distribution and complete the missing data, complete the data, and then re-estimate your model, right? Questions? Questions? No, okay. So oh, this is 1109. There's no 2023. My mistake. What is the point of having a blackboard and pens, ballpoint pens? Okay. Anybody want to answer the first question? I've given you the answers. Okay. EM attempts to complete the data and estimate the model parameters with the now completed data. That's true, right? I should have colored the wrong answers. This is so. And it draws data by missing values in proportion to P of M given O, also true, right? Instead of, or you can do this in proportion to the completed in every possible way. So now we have 20 remaining minutes, and I want a couple of volunteers. Who is brave? Okay. So this one's easy, right? Let's skip this. So here, for example, if I'm doing a multinomial mixture, I've got these two guys. They are rolling dice, and there's a guy at the door who's just calling out the number, and he's not telling you which dice it came from. So now, for each number, there's an associated color. Unfortunately, you don't get to see the color. So what is the next step? What are we going to do? What will we do? And then? Maximize. No, but what are we doing with this data? We're completing the data, are we not? Please don't skip 3 steps. When you skip 3 steps, you will make mistakes every single time, right? You're completing the data. So when I complete the data, I'm assigning a color to it. What fraction of the time am I assigning color blue? What fraction of the time am I assigning the color red? Posterior probability, correct? In proportion to P of K given O. And so having done that, then I can, that's P of K given O, right? Easy. And then here's the beautiful thing, right? How many instances of 6 am I going to get for the blue dice? How many instances of 6 am I going to get for the blue dice? So let's forget the scaling factor, right? Yes, go ahead. P of 6 given, is that it? What is N? Is it the number of samples? But then not all of them are 6. So this is going to be, this is going to be P of B given 6 and 6, correct? So each instance of 6 is going to give you P of B given 6 counts. There are n6 instances of 6, right? So this is the count of 6. That makes sense? So P of K given O was this. And let's go back here. The count of 6 was proportional, was this guy. And so if I want the updated P of 6 given blue, it's going to be, this is the count of 6 for blue, right? I write this as C B of 6. That's how many 6s I've seen. from blue, right? Which?
1/6.
In this case, I have only one, but I have 3 dots. Don't forget the ellipses, right? And so I'm going to get, so P of 6 given B is going to be count B of 6 divided by all i's, count B of 5, right? All counts assigned to 6, which is going to be n6 times P of B given 6 divided by, what is that? I and I P of B given I. This is all possible things assigned to 6, assigned to the blue dice, and the numerator is how many of them are 6. Does that make sense? Right? Easy. And so that's going to be an updated formula, right? So the probability for the observation O for the kth dice, the numerator is the number of times that particular observation was observed, right? Which is NO times P of K given O. And the denominator is the total number of observations assigned to the kth multinomial. And what is the probability of having chosen the kth multinomial? This denominator here is the total number of times the kth multinomial was chosen. That's going to appear in the numerator here. And the denominator here is the total number of observations. That's it, right? So very simple. This was the easy one, Alex. Okay. Now, I need your bravery for the second one. Okay. So here's a guy who flips a coin and rolls a dice. And if the coin shows head, he calls out the number. If it shows the coin is tails, he calls out the number plus 1. You only get to see the numbers. What is the probability distribution for the dice, and what is the probability distribution for the coin? How would you go about it?
6-sided dice.
It's a normal 6-sided dice, but it's biased.
It is biased.
It is biased.
We know what the,
No, all you get is the collection of numbers.
in what way it's biased.
You don't know why. You have to estimate this. How would you go about this? Right?
Either 0 or plus cousins.
So wait. So Alex is okay. Go ahead. Yeah. So if you see the outcome 1, what do you mean?
1, 2, 0 plus 1 plus 10. So it's actually.
Why is not?
Okay, so let's simplify this, right? Suppose you saw an observation K. Let me just say, suppose I saw an observation, like some guy called out the number 5, right? What is it you're going to associate with it? What is the equivalent of the color over here?
Coin flip.
Coin flip, head or tails, right? So if I saw a 5, then what are the possible outcomes?
5,
Yeah. Tail. And what fraction of it goes to 4 and tail?
Is it a regular coin?
No.
Oh.
Of course not. Everything is weighted.
Everything is weighted, right? So what? So okay. So what fraction of it is going to be 4 and 10? Anybody? What fraction of it is going to be 4 and 10? Okay, I can give you the answer, or you can work it out. P of tail given 4, yes. Okay. Yeah. P of
5K.
tail given 5, right?
Yeah. I suppose really we find these things a bit more careful.
Oh no, so this is not a count of 5. This is a count of 4, right? So okay, let me write this down. Let me help you guys. So how many ways can I get 5, right? If I got a 5, I could have rolled a 5 if the coin was what? Head. And I rolled a 5, or I rolled a 4 and the coin was a tail. So, and I'm going to say count 5 equals the number of times I rolled a 5, right? or the number of times I was called a 5, right? Times P of heads given 5, correct? Plus number of times I called there's a count for 5, so I could have called a 6, right? P of tails given 6, is it? 4? Wait, no. 5. So how many times did the dice roll a 5? So if the dice rolls a 5, the dice could have rolled a 5 if he calls out a 5 or if he calls out a 6, correct?
So what is count of 5?
How many times did the dice come up with 5?
Okay.
Right? So the dice could have come up with 5 if he called a 5 and it was a heads, or he called a 6 and it was a tails, correct? So this is going to be N5 times heads given 5 plus N6 times, yes.
Head given 5 and tails given 6.
Is heads given 5 P heads?
Because those two things are independent of each other.
Not really, right? So here, I'm going to complete the data here. The probability of heads given O is going to be how many ways? Suppose the guy calls out heads 50 times, right? Was it, so suppose the guy calls out 50 times. Was it heads every time? No, right? So it's going to be this, P of O times P of heads.
But they're not mutually exclusive, they're just independent.
Look at the denominator, right? So it doesn't mean, it also depends on the dice. If the dice never rolls a 4, suppose I have a loaded dice and it never rolls a 4, right? So anytime he calls a 5, what can you be sure of?
And it was the tails.
And this has nothing to do with the fairness of the coin, right? You have to account for the dice, right? So did this formula make sense here? Right? And so easy. So I can easily enough, I can count this guy. And so P of tails given O is the other side, P of O minus 1 given tails, right? Times tails, yeah.
Counting the number of times we're seeing 5, right? So you see 5.
Not number of times I saw 5, number of times the dice rolled 5.
So if a tail, like if you roll a 5 and you got a tail, then you observe 6, right?
Yeah, yes, so the number of times the guy called a 6 times the probability the heads was tail, the coin was tails given 6. This is the same as the dice rolled a 5.
Okay, but
Right? So
that be tails given 5 then.
no, because if the guy calls a 6 and it was a tails, then the coin was a 5. The dice was a 5. Right? Yeah. So again, I just made it a little complicated just to give you the idea of it's not, I mean, there's nothing particularly hard about this problem. You just have to twist your head around, right? But again, and then the rest of the formulas is straightforward, right? The probability of any observation is the count, right? Which is this one. So this is going to be my count for 5. I can get the count for each of the sides and re-estimate my dice. Problem solved, right? That makes sense to you guys, Alex? Okay, you miss it. Thank you for your bravery, right? So somebody want to do the next one? One of you guys? Hari, you were very energetic. Okay, now you're no longer sleeping, yes? This time I'm going to sit down and the rest of you help him, right? So again, did this make sense? How we went about solving it? Right? So this one, and so of course, the P of heads can be easily computed. Now, this is a slightly more complex problem. The guy is rolling 2 dice and he only calls out the sum. And both dice are loaded, okay? I want you to estimate the probability distribution of both dice. Fly, go away, go ahead, right?
So let's have a nice day, dice three.
Yes. So what I'm missing is the color of the dice, right? But it doesn't matter, yeah.
So let's first talk about
I want to move from top.
Okay, anybody want to help him? You guys? The solution is on the next slide, but I want to see how far you get. At 319, I will show you the solution. Where do you even begin? Where do you even begin, right? What is the missing data? The first thing you have to do, you have to identify the missing data, right? And then you've got to say, what are the possible values for this missing information, right? And then you want to compute the posterior probability for this missing information for each outcome. And that's the proportion you're going to be assigning to each of these values, each value, correct? So what is the missing information?
What the missing would be what you get in die 1 and what you get in die 2.
Okay.
So the count of that would be number of times you see A plus B. Probability that you get A plus B given that one.
That's going to be 1. Okay, Alex, go ahead. Help him.
I'm thinking like instead of that, we need to figure out so this can happen when I do some.
That's, yeah, they're beginning to get into heuristics over there, right? Okay, but this is a very simple EM solution. It's like a 2 equations, 2 lines of Python. So how would you do this? Okay, Hari, I'll give you a hint, right? So consider any possible outcome. So let's just take an example that he has called out the number 7, right? So if he has called out the number 7, you have the dice 1 and the dice 2, correct? What are the different combinations?
6.
1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. Okay. What is the posterior probability of this combination given that he's called 7? Isn't that what you want to compute? P of 1, 6 given 7. No, that's not it, right? Because here, so what is that are you looking at? Yeah. Why is there a given 7?
So like he has called out a 7.
What is the posterior of 1, 6?
Probability of that you get 1, 6 so that you given that he has called out.
Is that right? Okay, so let me help you guys. So stay here. Would this not be P of 1, 6 divided by P of 1, 6 plus P of 2, 5, and so on? Right? So where's the given 7? There is no given 7, right? The denominator is P of 7, which is the total probability of all these combinations.
So this one would be.
So this numerator is this probability of this combination. The denominator is the total probability of all combinations. Right?
This would be P of 1, 6 given 7.
This is P of 1, 6 given 7. Right? Similarly, I can compute the posteriors for each of these. Okay. So now let's just say that you have got the number 7 n 7 times, right? How much does this contribute to the count of 2 for the first die?
P of n7 into P of
P of 2, 5 given 7. So C2 of 2, or C1 of 2, right? So this is how much you got to count from 7, right? Plus n8 into P of 2, 6 given 8 plus n
6 7.
P of 2, comma 4, given 6, and 7, and so on. Does that make sense? You're going through, you're computing the counts for every possible value of the variable, that random variable, right? Through all possible combinations, and then you can just normalize. It's not even particularly hard. You just have to think about it, right? Again, that makes sense? Right, so that makes sense to you? Yeah. So again, the key was finding out what it is you're counting. And once you separate out all of the information and you count things properly, the rest of the formula just fall into place. The first dice information is missing, so assign to it every possible value, right? So P of n, comma, O minus n given O is P of n times P of P1 of n times P of P2 of O minus n, plus sum over all 6 Pm P of O minus n, right? M can take any value. And then once you have those, then you have the counts. You can just sum things up, right? Easy. So you're done. Thank you, Harry.